And it might even be possible that you'd have to like be in some master's program to be able to kind of go deeper on this. This is like the physical science level of this stuff, like in comparison to advanced chemistry. So remember in physical science how frustrating it was when I couldn't really explain anything. I just was here's a vocab word, here's a vocab word, here's a vocab word, and I can't really explain anything because you guys don't know anything.
Yeah, that was frustrating.
It's frustrating. It's frustrating as a teacher.
I asked you a lot of questions that you couldn't.
I knew the answer.
Yeah, but you couldn't explain it to me. You didn't have a back.
Yeah, you didn't have a good enough background.
Chemistry builds on.
Yeah, and so they would kind of get into the same idea here. This is really the first time we've really started to dive into this stuff, and we're really kind of at a physical science level. Maybe a little higher than that because we have at least a little. I'm not saying we're dumb. I'm saying the complexity of this stuff, we're just touching it right now. Okay? So don't feel like, oh my goodness, I have no idea, because I wouldn't say that my knowledge of this is far, far superior to your guys's. Okay? I remember as a chemistry major, I didn't really get any further than we are getting right now in this area. Okay? Probably if you really wanted to get more into this stuff, you want to go to some sort of quantum physics or quantum chemistry specifically. Okay? So, but still good to have kind of an overarching broad view of what's going on here. So, we are going to talk a little bit more about Bohr, and specifically how he came up with his energy levels. If you remember, Bohr was the first guy that theorized that there were different energy levels, which really he was kind of the first guy that he was really probably. I'm just trying to think. I don't want to misspeak and it not be correct, but I'm thinking, this probably was the beginning of quantization. Because to get from one energy to another energy level, remember how we've talked about before, like, and I know this is not the best description of it because they don't orbit like planets orbit the sun. Let's say that's your nucleus, here's your first energy level, there's your second energy level, but electron will be either here or here. It will never be in the space between. What do you think that's referring to? Yeah, the packets of energy, right? I cannot hang out somewhere in here. Okay? Because energy is transferred in packets or amounts of energy, I have to give it enough energy to be able to get all the way up to energy level 2, not somewhere in between. Okay? So I don't know. I'm trying to think of when exactly the whole quantization was really realized. But I think Bohr was on the cutting edge, even though he really didn't understand why. He was really the first guy to kind of realize, for some odd reason, it actually appears to be jumping with specific energies as he looked at the light spectrum that was emitted when an electron jumped to energy level and went back to its stable state, giving off energy in the form of light. Okay? So, pull up your book. Let's sit in 295 here. This first stuff is, unless you've had any physics background, and even Emily probably doesn't have enough physics background to really kind of comprehend some of this stuff, but Mr. Bohr, he was a Danish physicist, okay? So what he essentially did is he looked at varying energies of a hydrogen atom and how its electrons gave off certain electromagnetic radiation. And from that, he was able to deduce this idea of energy levels. And because energy was only given off under certain wavelengths, and therefore it wasn't like a stream of light, it was under only specific wavelengths of light. Okay, so I'm going to start reading here. Where do I want to start reading? Let's just start in 7.4 here, talking about Mr. Bohr and his model. Okay? 1913, Danish physicist Niels Bohr, aware of the experimental results we have just discussed, developed the quantum model. Bohr proposed that the electron in a hydrogen atom moves around the nucleus only at certain allowed circular orbits. Okay? He calculated the radii for these allowed orbits by using the theories of classical physics and by making some new assumptions. From classical physics, Bohr knew that a particle in motion tends to move in a straight line. Makes sense? Okay? And can be made to travel in a circle only by application of a force towards the center of a circle. I don't know if you remember, Emily, at all, centrifugal force and all of that. How if you're moving in circular motion, you have to have some sort of force towards the center of that motion in order to get it to actually go in a circle. Otherwise, particles or things tend to go in a straight line. Make sense? Okay. Thus, Bohr reasoned that the tendency of a revolving electron to fly off the atom must be just balanced by its attraction to the positively charged nucleus. But classical physics also decreed that a charged particle under acceleration should radiate energy. So he had a problem. Now you guys won't know this if you didn't take physics, or haven't taken physics yet, but a particle that is changing directions is always accelerating. And what they're saying is, if a particle is already accelerating, what they know from classical physics is that it would be losing energy as it continues to accelerate. Since the electron revolving around the nucleus constantly changes its direction, it is constantly accelerating. Therefore, the electron should emit light and lose energy and thus be drawn into the nucleus. Well, we know that doesn't happen. Right? We know that electrons aren't losing energy being drawn into the nucleus. This, of course, did not correlate with the existence of stable atoms. Clearly, an atomic model based solely on the theories of classical physics was untenable. Bohr also knew that the correct model had to account for the experimental spectrum of hydrogen, which showed that only certain electron energies were allowed. Energy level 1, energy level 2, energy level 3, quantum packets of energy. The experimental data were absolutely clear at this point. Bohr found that his model would fit the experimental results if he assumed that the angular momentum of an electron could occur only in certain increments. So he didn't know why, he had no idea, but he said if the momentum of a particular electron can only happen in packets of momentum, everything works mathematically. And he had no idea why, but it's like the only way for this to mathematically work out is if I assume this. Right? It was not clear why this should be true, but with this assumption, Bohr's model gave hydrogen atom energy levels consistent with the energy emission spectrum that they were seeing when light was given off when an electron lost energy. Okay? So he came up with an equation. Here it is. Right here. This is probably, and it says in your book that like this is probably the most important equation that he came up with, and it says we're not going to derive how this equation came about at this time. It's too complicated, blah, blah, blah. Here we go, physical science all over again. Anyways, let's look at this. From past things that we know about the symbol N, we should remember that N really represents energy levels. I don't know if you guys remember from regular chemistry when we talked about principal energy levels and how there were 7 principal energy levels, and those energy levels were represented by N. Energy level 1, energy level 2, 3, 4, 5, 6, and 7. Okay, so if I'm at N of 7, I'm at the 7th energy level, I'm also probably have the most electron energy available because it's further away from the nucleus. And the only way it got that far away from the nucleus is because it had a high amount of energy. Okay, so just remember, lower energy level, closer to the nucleus, less energy. Higher energy level, further away from the nucleus, more energy. That should be reviewed, but just making sure you're aware of that. Z is your nuclear charge, or essentially your atomic number. So your atomic number is going to be your nuclear charge. Okay, we're typically going to be just dealing with the hydrogen atoms, electron spectrum, and energy associated with the one electron within a hydrogen atom. So most of the time, this Z is probably just going to be 1. But be careful. If in your homework it says, what's the energy difference between energy level 2 and energy level 4 for a, I don't know, potassium atom, then you have to put 19 in for the Z. Okay? Let's, why is this like so bad? Wait a second. I don't want to do this one yet. I don't know if you have space for an example before that example. What you're saying. Okay. Just watch this then. Okay, so we're going to an electron from N is 6. Okay, electron was excited at energy level 6. Falls back down to its ground state. What's the change in energy? That would be required for an electron that got excited to the 6th energy level, is unstable, falls back down to the 1st energy level. It's going to give off a certain amount of energy, and we could actually figure out what wavelength of energy this would give off, what color light this would actually give off. Okay? So we've got a couple things we can solve for. Energy level 6, energy level 1. We can figure out the energy associated or needed to be in energy level 6. The energy required or needed to be in energy level 1. We can find the difference between the two, and that would be how much energy would be released going from 6 down to 1. Following? Okay. U6. We're talking about a hydrogen atom. So Z is 1, 1 squared is just 1. And what number goes here? Okay, I want you guys to solve for that. Now, E of 1 is just very simple. It's this. What's E? E of 6.
Negative 6.05 times 10.
Okay? So we want to figure out how much energy is going to be given off going from energy level 6 down to energy level 1. Change in E would be final minus initial, correct? What was our final state? You guys understand where I got this number from, right? Okay, if it would just be 1 squared over 1 squared, it's just 1 times that. Okay, so what you're going to see here, guys, is that going from energy level 1 to any other energy level will always be some multiple of this number. Packets of energy. Okay? It will never be a number that's not a multiple of this. Minus negative 605 times 10 to the negative 20. The answer for this is negative 2.11 something. 7. could I take this energy that this electron gives off, go down from energy level 6 back down to energy level 1? Could I figure out the wavelength of light that this will be emitted at? Because we could probably figure out what color of light this would be given off as. You guys remember probably way back when we were in physical science doing the flame test and we burned certain things and they gave off really interesting colors. What that was, we were exciting electrons up to a higher energy level. The electron didn't want to sit in this really high energy level, it wanted to go back to stable, so it went back down to its stable state and gave off energy in the form of light, and the color light was based upon what energy level it was in, what substance it was, and how much energy it gave off, and what wavelength.
Is that way different
Fire.
temperatures of fire for different colors? The hottest is like blue flame and then
I don't know, I'm not sure.
yellow.
It could be right, because I mean, the hotter the energy, the more energy, the hotter you burn something, the more energy it has, and so maybe you'll be able to get to a higher energy level. That's
More to get
possible.
rid of.
That's very possible. I've never really.
Maybe it's like the oxygen burning or something, releasing energy, and the outside is something else.
I mean, it makes sense theoretically in what I know, but I've not really looked into it enough to know yes or no for sure. Okay? And that's going to be negative. Why? Why is that going to be a negative amount of energy? It's being released. So if this were flipped, if I were going from energy level 1 to energy level 6, it'd be the same amount of energy, but it would be a positive amount of energy needed to get it up to energy level 6. Make sense? In versus out kind of idea here. So,
But the question asks, how much like does something the surrounding gain would be positive, right? Because it's surrounding.
well, here we're talking about
I know.
going from a high energy level to a lower energy level. We're just talking
So
about
it's the system.
overall energy, yeah, the whole
But
thing.
if it didn't ask for the surroundings, we'd use this to solve for energy to the surroundings, it would be positive.
I suppose we're not going to do that.
Oh, okay.
All right, so I want you to try to do this one. Now notice, it wants you to know how much energy required to get from energy level 1 to energy level 2. But then it also wants you to calculate the wavelength of light that must be absorbed in order to do it. Essentially, we're talking about the photoelectric effect. In order to get an electron to jump an energy level, how much light energy needs to be absorbed, and at what wavelength and frequency would that need? The E of 1, you guys should always know, it's just that one number. Got them already in there?
So,
Got your change in energy and your wavelength? We'll give you guys a few more seconds.
-10 to the -19.
Sorry, I'm gonna ask answer.
Yeah,
What's
I
Griffin?
got that too.
What?
10 to the negative 19.
Oh. Did I mess that? Yeah, you're right. My bad. What? What was your question?
What equation do you use to solve for?
Well, you want an equation with energy in it. Okay, you don't have frequency, and so it's going to probably be Planck's equation, just substituting in wavelength and speed of light for frequency. So,
What,
Your-
change the E to HV?
well, hv, but you're replacing v with the speed of using the speed of light. You're substituting in to get wavelength and c in there. Does that make sense?
You don't have B, so C over.
I think you guys have that equation.
Yes.
Probably.
It says like
Right there.
change in E equals H.
Yeah, I found it, yeah, photons, even photons.
Yeah, energy of a photon. Yep. So we're talking about a photon here. We're talking about a specific electron is our photon, right?
The constant is H, right?
Yeah. H is your Planck's constant that was derived when they realized the whole quantization idea. So final minus initial. Final would be your E2. And in a sec, I'll give you an equation you can probably use a little bit easier than doing all of this. Notice how this number is positive. Someone tell me why this is positive. Yeah. Okay, that's your change in energy. That would be the amount of energy that you would need to jump from energy level 1 to energy level 2. Okay, and then you're going to use that with this equation to find your frequency or your wavelength. Now, once you had your wavelength, could you also find your frequency? And what would that frequency be?
C times sigma.
Yeah. But what that specific frequency, we would call that the threshold, right? That makes sense? That would, because this is the minimum, this is going to be the wavelength that would be required. Well, remember, there's a fundamental threshold of frequency that unless we're at that frequency, this electron's not going up to energy level 2, is it? Okay, so we can take whatever we find for wavelength here and plug it back into the speed of light equation to figure out what the fundamental frequency is. What did you get, Grant?
Do it in nanometers or meters?
I'll take meters, it's fine.
1.22 times 10 to the negative 10.
That's how
That's right. Did you get that, Emily? Andy? What'd you do there, muchacho?
I multiplied the speed of light times Planck's constant and divided by the 1.6335 and 10 to the negative 18.
And you must have did some lack of parental guidance. Parenthesis guidance. I'm guessing, because it sounds like you set it up correctly. Okay, I want to get to this next one here. I think you just had some sort of calculator mess up. Griffin Brothers, you guys get all that?
3 times 10 to the 8th, right? Is the speed of light?
Yeah. You need everything in parentheses, probably.
Yeah.
Now, did I give you in your notes a different equation anywhere? You didn't. All right. I'm going to give you this guy. Probably a little bit nicer equation.
I got it right.
Still?
No, I got still.
So this equation that I'm just giving you is going to be taking the change in energy and putting it into one equation. So you now have to find the energy for the first, and you don't have to find the energy of the final and initial, and then to find the change. You're just going to do it all at once here. Now this is, it's important here that this is specifically for hydrogen's electron. Why do I say that? Yeah, because so here what we're doing is we're taking, this is the change in energy associated with whatever energy level you're going from. So if I'm going from energy level 1 to energy level 6, that would be the change in energy. What we used, that other equation that we were using was just what's the energy associated with a specific energy level. Does that make sense?
So if there's a different.
We could have used this to solve the other two problems we just did in one equation. So what we previously did is we said, oh, I know here's what the energy is of the 6th energy level, here's what the energy is of the 1st energy level, here's the change in energy. Is E6 minus E1. This is doing all of it at once.
It wasn't hydrogen though, because you just plug in hydrogen.
What was that?
Like if it was lithium, P103.
Probably. I'm assuming they're only going to do hydrogen because it's just the most basic. But yeah, you could change that to whatever the nuclear charge
Or that
is.
should be 9.
What was that? Lithium would be 9. Well, 3 squared, yeah. Okay? Now, it says, calculate the energy required to remove an electron from a hydrogen atom in its ground state. Now, here's we're getting a little theoretical here. Okay, so we're going to go. Okay, if I'm removing an electron from the ground state of a hydrogen atom, what energy level am I in? If I'm removing an electron from an atom, completely removing it, am I really in an energy level? So we'll say it's an infinite distance away. Minus,
So that's 0.
yeah. So I want you to realize is if we solve for this, okay, the only thing is this is going to be essentially what? 1 divided by a huge number is what?
0.
Pretty much nothing. Okay? And then I'm going to take this number and multiply it by -1. So how much energy does it require to remove an electron from the first energy level? The positive amount of energy that's holding it there. Does that make sense? Okay? We know that the first energy level has this much energy. So if I want to remove it completely from the atom, I'm going to have to apply that much energy to remove it. Does that make sense? No? I think it should? Yeah?
It should be positive.
It will be positive, yes. Because if you're going to remove an electron, you're going to have to apply that much energy to it. So it would be 2.178 times 10 to the -18.
So if you're not removing from its ground state, like from
We could say, hey, how much energy would be required to move from the 6th energy level? Well, we just have to find the energy associated with the 6th energy level, and then that same amount of energy just to remove it. And it should make sense that it's going to take more energy to remove it from the 1st energy level than from the 6th energy level. Because remember, what was the amount of energy in the 6th energy level? It was like, what was that number?
-6.05.
Yeah, so this is how much energy would be associated with the 6th energy level. Notice how it would not take as much energy to remove it out of the 6th energy level as it would out of the 1st energy level, because you're further away from the nucleus and it already has a higher energy state.
So if you're solving for it, taking out the 6, then you just put 6 for the 1?
Yeah.
Like 6 with
Yeah, you put a 6 here.
Yeah.
What if the second one is 0? Like the final
So you didn't do that.
crash or remove the electron from hydrogen?
Isn't this final minus initial?
So that, okay, yeah.
That's change.
Why is that infinity though? Why not 0?
Well, that's what 1 divided by infinity is 0.
Yeah.
saying why isn't like, you're saying like why isn't the end defined at 0?
Yeah. It has no energy level left.
With the energy level.
Well, can you have a 0 energy level? Energy level is just a theoretical number for being able to figure out how far away it is. I understand that,
But why do you use infinity?
because it's really far away. I mean, if you take an electron away from the nucleus, you're really far away. Right? I mean, you're nowhere near the nucleus of a particular atom if something is taking it away. Now, could it be 500 meters away? Could it be 3 million meters away? We have no idea. But the point is, there's a certain point where it's far enough away that there's no energy associated with regard to the nucleus.
Okay.
Good morning. Good morning.